guys, this is going to be our makeup lecture for curve sketching, which is the tail end of the section that we just started last class on concavity. So, just as a refresher on where we've left off over the last couple days, this is where we're at. We've talked about the first derivative test for local extrema. This is something that followed our test for global extrema. This let us look for local maxes and local mins of curves, this test right here. And then we followed this up most recently with my second derivative test for concavity. Now, just so you guys have all of this in one spot, I wanted to give you guys a recap of the steps for both of these tests because we're going to need them, or at least ideally we need them, to figure out stuff that's going on in this curve sketching section. So, without further ado, I'll go ahead and start. First off, in this, let me make sure that I've got my pin going straight here. First off, for the first derivative test, you wanted to start this guy out looking for critical points, right? So basically step one was find my critical values and also my spots where my derivative, my first derivative, did not exist. Reason that I was looking for all of these is that I wanted to mark these on a number line that was supposed to be representative of my domain for my function. You probably want to differentiate between the spots where your derivative doesn't exist and happens to not be in your domain versus your critical points, which are always in your domain. These can split up places where you increase versus decrease, but they won't necessarily be locations of extrema. At any rate, mark all those on a number line. Once you have all of those guys marked, you wanted to check your test points in your first derivative of your function, and the reason that we were looking at these was for sign. Okay, positive was going to tell you increase, right? So I'll go ahead and note that here. Positive tells you that you increase, negative tells you that you decrease. Okay, and then from here we wanted to determine the locations of my extrema. If I have something that looks like a local maximum, like this guy, it's because I increased, hit one of my critical points, and then I decreased. Or, on the other hand, if I have something that looks like a local minimum here, the reason that I got that is because I decreased, I hit my critical point, and then I increased. So, the idea of the first derivative test was to use whether or not your function was increasing or decreasing, or vice versa, to determine the locations of your extrema. Now, what we were looking at more recently, on my second derivative test for concavity, this looked super similar here, except for we're doing all this stuff in the second derivative. So here what I'm looking for is basically find my spots where my second derivative was equal to 0 or did not exist. Again, you would probably want to differentiate these on your number line somehow, but at any rate, the next step was going to be to mark these on a number line. After this, we are going to check test points, but here's where my tests differ. We are checking my test points in my second derivative, not my first derivative, but we wanted to check these guys for sign in my second derivative. Now the difference here is that if you got a positive, this meant that you were concave up, and if you got a negative, this meant that you were concave down. Okay, so basically here we don't really get extrema for this particular test, but I could note that you know, if my concavity switches, if this is at a spot in my domain where I have a tangent line, so in other words, my second derivative, you know, I have to be able to take a tangent line at a location where that guy came out to 0. If my concavity switches at a point in my domain, I'm going to get an inflection point. Now the simple thing about this is that I didn't have to worry about keeping track of whether it went from positive to negative or negative to positive, just if it changes at all, positive to negative or vice versa, we've got an inflection point. Okay, so let's see if I can go ahead and apply all of these to a example. I'll switch over to my next slide here. Let's see if we can find my intervals of increase and decrease, and my intervals of concavity, and also my locations of local extreme and inflection points for the following function. So I'm asking for a lot of information here. We're going to get real thorough with this function, but really all I'm asking you to do is apply both of those tests. All right, so I'll do this in the order that we learned them. If I want my first derivative test, this is going to tell me my information on whether I'm increasing or decreasing and whether I have extrema or not, right? And this is all based off of information from the first derivative. Your steps here were to find critical points. We do this by taking the derivative, which I'll go ahead and compute here super quickly. We take this derivative and then we set it equal to 0 to find those critical points. So if I set this guy equal to 0, I can factor out a 3, get 3 times x squared minus 4, that equals 0. And you may notice that this is a difference of squares. When I factor that, I get x plus 4, x minus 4. So I actually get 2 critical points for this particular function, right? Actually, minor error here. Let me get this straight. If I take my factorization, plus 2 minus 2. Whew, glad I caught that. So 2 critical points for this, now that we actually got them straight. Plus or minus 2. These are the critical points that I get for my function. Sorry about that small mistake, guys. So at any rate, these guys are my locations of critical points. These are the things that I wanted to mark on my number line. So here I will stick -2 and I will stick 2, and these were both of my critical values or critical points for this function. After this point I need to pick test values to plug into my derivative, right? So I could pick something like, let's say -3, I wanted to test that guy. 0, I could test this guy. 3, I could test this guy. And I'll go ahead and scroll down a little bit to give myself some more room. All these things are going back in my first derivative, right? So I basically needed information on f prime of -3. I needed information on f prime of 0 and on f prime of 3, because these were my test points. Now the function these are going into is up here, 3 times x squared minus 12. So I'll note this gives me 3 times 9 minus 12, 0 minus 12, and again 3 times 9 minus 12. You know, I can actually crank out each of these values, but really the most important thing is just what the sign is. I'm coming out with something like 27 minus 12 here. Who cares what that actually comes out to? The key thing is that it's positive. 0 minus 12, the key thing is that that's negative. And 27 minus 12, again, the key thing is that when I get 15 back there for both of these top and bottom values, that it's positive. Because I need to take these guys back to my number line to make note of that information. Anytime that your derivative is positive, you're going to be increasing. So I'm increasing on these outer intervals. Anytime that your derivative is negative, you're going to be decreasing. So comment number 1, I'll scroll down to give myself a little bit more room. You know, I can go ahead and note that for my intervals of increase and decrease, since that was requested, I increase on -infinity to -2 and on 2 to infinity. Similarly, I decrease on that middle interval from -2 to 2. Okay, if I wanted to know where my extrema were, we can go ahead and note that anytime that you switch from increasing to decreasing, you're getting bigger and then smaller. So we have a local max at x equals minus 2. And similarly, but in the opposite direction, we are going to get a local min at x equals 2. Now that wraps up all the information that we get from this particular function from the first derivative. And if I scroll back up super fast, okay, we wanted intervals of increase and decrease, and we also wanted locations of local extrema. We got those. Last thing that we needed was concavity information and locations of inflection points for this guy. Okay, well, notice you need the second derivative test for that. So I'm going to go ahead and get that information started down here. For my second derivative test, this is going to give you information on concavity and inflection points. So you need your second derivative. I'll scroll up just high enough for us to remember what that was. F prime was 3x squared minus 12. I will copy that back down here. Okay, f prime of x is 3x squared minus 12. For your second derivative test, you have to take a second derivative. So I'll go ahead and do that here. If I take my second derivative, I will get 6x, just 6x by itself. We said that we wanted to set this guy equal to 0 to figure out what points that I needed to mark on my number line. There's only one point here. I just need to mark 0 on my number line. That's it. You know, I could still pick test values kind of like I did before with my number line above, except for the catch is, and I'll scroll down and give myself some space here. The catch is that these guys are going to go into my second derivative because this is my second derivative test, not my first derivative test, right? Now, we have f double prime up here. That's what these things are getting plugged into. I've got basically 6 times minus 1 up here and 6 times 1 here. And this is going to be negative 6 and positive 6. The whole focus of this is, again, where is this guy negative and where is this guy positive? Because what this is going to tell me is my concavity, right? If we are negative, we are concave down. You know, concave down like a frown. The curve opens so that it curves downward. And if we are positive, we are concave up like a cup. So if I wanted to break down my interval information here, you know, we're going to be concave down on the interval from minus infinity to 0. We're going to be concave up on the interval from 0 to infinity. And again, recall, if you switch concavity, this is going to tell me that I get an inflection point at the location x equals 0. If you actually want the full inflection point, you know, you can go ahead and take this coordinate, plug it back into this guy, plug it back into your original f function that we gave us, that cubic polynomial. Get a y coordinate to pair with this for my actual point on my graph or my point of inflection. But at any rate, this is the information that I requested from that original function. We found our extrema, we found our inflection points, we found we were increasing and decreasing and what our concavity was. Now, why would I want to sit here and figure out all this stuff for a particular function? Well, here's kind of my general point for today. This was the curve sketching section, or I said that we were going to follow up concavity by thinking of this as the curve sketching section. The idea here is that we want to use the information from the first and second derivative tests, and also potentially some information that we knew on limits before, to sketch important features on graphs. Now, I know what some of you guys are thinking, I can just stick this in my calculator and it'll tell me what the function looks like. Why do I have to go through all this work? Well, I'll give you guys kind of a sort of dumb example here, but just because you see what's in the viewing window for your calculator, you know, let's say here is my viewing window for a particular function, you know, that I've graphed on on my calculator, and I'm interested in where this guy has extrema, or, you know, where it's curved up or where it's curved down, and I get this nice little function that does something like this, and then it keeps going. Well, how do you know what's outside of your viewing window, right? How do I know that, you know, maybe if I zoom out far enough, maybe I get some really crazy behavior in my graph that I'm not immediately seeing because I'm not zoomed in the right way. Conversely, you know, how do I know that maybe if I zoom into a really tiny little box here, that there's not some sort of really erratic detail happening where I get other local extrema, other local maxes and mins that I'm not seeing just because the scale isn't big enough, right? Unless you purposefully know to look for these kinds of behaviors on your graph, you could get all sorts of crazy stuff that, you know, will never even cross your radar if you just don't happen to pick the right zoom window. Now, the trick to getting around this is going to be basically use calculus, right? We've got these methods, you know, like the first derivative test and the second derivative test, that'll give us information on the shape of a graph. And you'll note, for that example we just did, I didn't need to pick a zoom window to find my extrema. You know, the calculus just told me the information that I was requesting on my graph. Where are my maxes? Where are my mins? The test pops it out automatically, okay? So we can avoid finding these weird, you know, situations that we don't know about as long as we analyze the function using the tools from this class. So how do I more rigorously use those tools? Well, there are a couple of basic steps that we think of for curve sketching. And the first one of those is just going to be to collect all the information that you can on the function. Now, this is us using the tools that we already have in our toolkit, right? From way back when, we can analyze asymptotic behavior using limits at infinity and limits that spit out infinity. So remember, divide by zero errors are probably going to give you vertical asymptotes. If you have a limit out at infinity or negative infinity, that'll give you a horizontal asymptote. We just found information on checking these intervals of increase, decrease, concavity, locations of extrema and inflection points. I'll go ahead and note, if you find x values for either of these things, these extrema or inflection points, you can take this back to the original function f and plug it in to get a y value. So if you needed full coordinates for that point, maybe you wanted to plot those points of interest on your graph next, you can, right? Find the x values of points of interest, take them back to the function, and now you got points to plot. One of the next things that you can do is, after plotting points, maybe I should specify here, you can also plot your asymptotes if you have any. After you've got those points and asymptotes, you can play connect the dots with those points that you just plotted on your graph. Now be careful about your behavior of asymptotes. Those may give you some other dots to plot down, but at any rate, once you plot those points and play connect the dots, the concavity information is going to tell you how to round out the curve. Okay, so this is basically just me checking, is this concave up? Is this concave down? And if I'm playing connect the dots, you know, hopefully what we can track there is make sure that this matches your increasing and decreasing information. Okay, so I'll give you guys an example. Actually, this is the one that we just did, and this was the information that we returned, right? My first derivative test basically told me that I was increasing, then I was decreasing, and then I was increasing. So in general, my graph is going to have a sort of zigzag shape. If I want to round this thing out, I can notice that being negative is, in my second derivative, is going to make me concave down, and being positive is going to make me concave up. And hopefully this sort of pairs up nicely with this graph up here. You know, we can open upwards pretty easily on this region of my number line, and we can open downwards pretty easily on this region of my number line. But let's formalize my steps here, right? First thing that it said was collect the information. We already did all of that. The next thing that you want to do is plot important points. Now, I'm going to go ahead and make the observation that these guys were pretty important x values for us in that last section. We had a local max, a local min, and then an inflection point on my graph. So I probably want full-on xy coordinates there. If I go ahead and plug those x values into my function, I'm going to return the following coordinates, okay? I will get, let me actually get 0 first over here. If you plug -2 into this function, well, that'll give you -8. This will give you +24. And that -8 is going to cancel with this guy. So you'll basically be stuck with the +24 over here. 0 is a little bit easier to plug in. Those terms will knock off, and you'll just be left with the 8. And similar idea over here. If I plug in 2, I'm getting 8. -24 plus 8. Those positive terms are 16. Subtracting off a 24. I will get a -8 down here. So these guys are going to be points on my graph. Okay? And I'll scroll down and give myself a little bit more room here. I just need my graph to match this information. So we said that we are going to have this point at -2. This is obviously not to scale. 24 up here. We have this point at 0, 8 right here. And we also have this point at 2, -8 down here. So step number 1, was obviously collect information. Step number 2, let's plot my important points. I'll try to color code this guy here. I'll do my next step 3 in red. We wanted to play connect the dots. Now again, what connect the dots needs to do is it needs to match my information from my first derivative test. So not only do I kind of want to note that, okay, I'm probably doing something like this on these intervals. Does this match what I said was happening on my sign chart up top? Now, on the interval from -2 to 2, we said that we were decreasing, and sure, that makes sense. My dots that I connected decreased. What am I doing on the other intervals? Well, after 2 I'm increasing, so my function has to be getting bigger. I'll go ahead and play connect the dots over here. And similarly, before -2, my function had to be increasing. So it had to be getting bigger until it hit that point at that end point. So I'll go ahead and draw some dots over here. Now, the reason that I drew this with a dashed line is because this is not going to be the final version of your function. I'll do my final version in, let me get my color actually straight here. I will do my final version of my function in blue. You actually want to round out your curve. So what I mean there is pay attention to your concavity, right? If I'm looking at my number line, say for example on this interval from 0 to infinity, after 0, you have to be concave up. That means after 0, your function has to be rounded so that it looks like it's curving and opening upward. Remember, concave up like a cup, okay? So, for all the positive values, I'm going to try and make sure that this thing roughly looks like it's curved so that it's opening up, okay? Similar deal for the back here. If I was to the left of 0, if I was on my negative x values, we said that we should have been concave down. So I need to make sure that I'm roughly following where my dots were, but I just need to make sure that I'm curving so that this thing opens downward too, right? I'm no longer following these I don't want to call them straight lines. They're not straight. My drawing was a little shaky here with this pen tablet, but I'm no longer following these dashed lines precisely, but I am trying to follow them so that I curve down and I curve up in the appropriate spots. So this guy, this is my final approximation of what my curve looks like. Okay? And you'll note, again, this is maybe not to scale, but the salient features are here. I know where my extrema are. I know where this is rounded out. So I know, where the important features are on my graph. I'll give you guys another example. Let's say that I've collected the information for some other function, right? Some other totally different function. And what's going to happen here is we just have to interpret all this information, right? So I know basically points that are going to lie on my graph. If they tell you anything about the first derivative, this is really giving you information for your first derivative test. And if they give you any information on your second derivative, this is basically filling you in on your second derivative test. So I can set up sign charts, for those guys. It seems like if I wanted to make note of my first derivative, they seem to split stuff off on my intervals from minus infinity to 0 and 0 to 4. So there's a nice split at 0 there. There's also a split from 0 to 4 and 4 to infinity. So there's another split there. What's the sign behavior that they just said? Well, f prime is positive on both of these intervals. Okay, so we can go ahead and note that. And f prime is negative on the remaining interval from 4 to infinity. We can note that too. Remember, your first derivative is going to tell you where you are increasing. Positive means increasing, and where you are decreasing. Remember, first derivative being negative means decreasing. This is probably also going to hint, hey, you probably can assume that you've got some sort of extrema here, at least if we assumed that the first derivative was 0, right? I'll go ahead and fill in this assumption just to make sure that my graph matches here, right? And let's go ahead and let f prime of both of those spots be 0. Okay? Then I know for a fact I can claim that this guy is a maximum, right? For f double prime, what information am I getting back here? Well, for this particular guy, the split seems to be happening at 0 and 2. We have a positive second derivative on the interval from 0 to 2, and we have a negative second derivative elsewhere. Now remember, that was the difference between being concave down and concave up, right? So these guys were concave down, that middle one was concave up. So let's see if we can, actually get some information straight here. I will try to remember when I scroll down, we said these were our important points. F of 0 is 0 and f of 4 was 3 that we needed to plot on my graph. So let's see if we can use that sign chart to help us sketch some stuff here. Okay. First off, we've got the info that was given to us. Second off, we want to plot my important points. There's no limit information given here, so I'm not going to assume any asymptotes or anything are happening. But I do know the origin has to lie on this graph, and I know that the point for 3 has to lie on this graph. Next thing that I wanted to do, I'll do this the same color that I did last time. We want to play connect the dots. Now this is where I'm tracking my increasing and decreasing behavior. We said on this interval prior to 0, we had to be increasing. So that means I'm getting bigger until I hit 0. On the interval from 0 to 4, I'm also increasing. So this is convenient. I get to play connect my dots between 0 and 4. After 4, we said the function was decreasing, so my function should get smaller after this point. Next thing that I wanted to do was now round out my curve to give a final version here. Now this is where we are tracking my concavity information for my question. So I can go ahead and note here there is this split between the interval from 0 to 2. So I'll go ahead and mark that guy here. Let's go ahead and stick 2 down. Between 0 and 2, we had to have a function that opened upward. Okay, so I'll go ahead and try to bend this little section of the curve so that it looks like it opens upward there. On the other intervals, though, we were concave down, so it looked like we opened downward. So I get to bend my function so it looks like it opens downward on each of those intervals. So I can do something like this. Okay? So in this particular case, this blue curve here, this is going to be my finalized version of my curve. Okay? Curves downward down here, upward up here, and then starts to curve downward again on this remaining interval. Okay? Let's try this for a slightly different example. This one will actually give you some information regarding limits. So here I maybe don't actually give you guys any information about particular points. Let's see if we can keep track of some of the information that's going on here, though. This will start off a lot like my previous questions with limits, right? My limit as x goes to 0 is infinity. So that means towards 0, I've actually got a nice vertical asymptote here. And as I get close to 0, so as I come in towards 0 from the left and towards 0 from the right, my function is basically blowing up. So I'm going to get an asymptote here. And for sake of playing connect the dots, I'll go ahead and let those guys be the dots that I connect to. Similar comments about my limits. As we go off towards negative infinity, my function approaches 0. That's going to give me a horizontal asymptote of y equals 0, okay, where my function is heading off towards 0. Give myself a nice little dot to connect to here. And similarly, as x goes to infinity, my function seems to close in on positive 2. This means I get another asymptote at 2 this time. Okay, as x blows up, my function closes in on that 2 value there. So we've got a couple spots where maybe I really want to play connect the dots. Let's see if they match up with the rest of the information. Right? So here I'll go ahead and still do this in red again. We have said that my derivative is positive if x is negative. So that means back here to the left of 0, my function's increasing. So sure, that makes sense. I can go ahead and connect my dots there. Similar deal on the other side. My derivative is negative if x is positive. That means I have a decreasing function if x is positive. So sure, that makes sense. I can connect my dots here. The final thing that I'm going to want to do is actually sketch out my curve as it's rounded. And we said that my second derivative is positive as long as we're not at 0. This is basically suggesting that we're concave up everywhere, and maybe we get a break at 0, which also makes sense, right? I can curve this very definitely so that my function opens upward and increases on this interval, and opens upward and increases on this interval, right? All I'm doing is rounding this guy so it looks like it curls so that it faces upward. And this guy here, with its asymptotes included, this blue curve should be a finalized draft of one option that'll, work for this particular function. Okay, we are going to change gears here totally and try a different example. This is phrased in a very different manner from how I've given you guys information and how we've started with functions and been able to process information, but we can still pull some information from our graph here. I just wanted to see you guys tackle something that's presented in a slightly different context. What I'm giving you right now is a graph of the function f prime of x, right? This is not a graph of the function f. This is a graph of its derivative. And you'll notice I'm asking you guys questions about f here. Now, I'm going to erase this in a hot second, but just to highlight the difference in functions that I'm demonstrating, I'll have you guys consider an example really quick. Consider, f of x is equal to x squared, which looks like a parabola, versus f prime of x for that same function, which looks like basically the function 2x. This is the straight line, slope 2 going through the origin. So what I want you guys to focus on here is kind of the situation that's happening is I'm showing you a picture of the derivative and I'm asking you questions about the original function, right? Now, notice if I were to ask you something like, where does f have a local minimum? Well, I can't look at this graph here and check for where this guy has any local minimums to get information on the local minimums of f, because this guy doesn't have minimums. So we have to think a little bit deeper about how we're processing the information that comes from this graph. Now, you'll notice here, and I'll go ahead and kind of start tackling part A in this question. Part A, we're being asked about extrema. Extrema is going to come from us doing a first derivative test. So really, I want to be making a sign chart using the information from this graph. Now, to pull from the picture that's going on down here, right? Anytime that we're getting a local minimum, we are expecting our function to decrease, okay, kind of like it is on this interval, and then increase. Now, notice decreasing means that your first derivative should be negative. In other words, we are checking signs here. My first derivative is going to be negative when it's below the axis, so that means decreasing over on the original graph. And my first derivative is going to be positive when it's above the x-axis, so that's going to correspond to increasing on my original graph. Okay? Now, for sake of me having some extra room here, I will go ahead and kind of scrap this little section and at least move him off to the side where he's not quite as much in the way. If I'm making my sign chart to figure out where I'm increasing versus decreasing in this particular function, well, first thing that you do when you're making your sign chart is you figure out where you have critical points. So where is your first derivative going to be equal to 0? This is a graph of my first derivative. So where's the output of this thing, 0? Well, happens right here, and right here. So that means I'm going to get critical points at 1, 3, and 5. Now, if I'm checking for signs of my first derivative, again, this is going to correspond to where I'm above versus below the x-axis, okay? If I plug in, say, for example, 2 to this function f prime that I've graphed, I get a negative number, right? If I plug in 4, I get a positive number, right? So I want to track this. Are we above or below? We're above on this interval back here, so I'll call f prime positive. We are also above on 3, 5, and we are also above on 5, infinity. The only spot where we're below is going to be basically the interval 1, 3. So what's happening here is we are increasing, we are decreasing, we are increasing, and we are increasing again. So if I'm looking for local extrema, right, keep in mind here is an increase, a decrease, and an increase. It didn't actually switch at this other location. This sign chart is going to tell me that we have a local max at x equals 1 and a local min at x equals 3. Now notice I am not trying to tell you the minimum is at 2 or at 5 or the maximum is at 4. This is totally not what we are doing here. What it turns out we're looking for is these x-intercepts for my derivative. They're going to highlight to me I am increasing here and decreasing here, so that means I get a maximum at 1. I am decreasing here, then increasing here, therefore I get a minimum at 3. I am increasing here because I'm above the x-axis, and then increasing here, that means I don't get crap at 5. Okay? Now I'll go ahead and actually delete this guy so I can make some room for me to answer part B over here. So we'll scrap that. Where does f have inflection points? Now, if I'm trying to figure out my inflection points for f, similar question, but this time you are making a second derivative sign chart. All right, well, that's all well and good, but I don't have a picture of the second derivative like I do the first derivative. I just had a picture of my first derivative. What gives, right? Now, here's the key observation. My second derivative is basically going to be a derivative of f prime, right? That's what this guy is, a derivative of f prime. That's how you take a second derivative. You derive your derivative. What's another word for derivative? Slope of f prime. This is another way for me to track my second derivative, is I'm really looking at the slope of this function that I've graphed here. So if I'm looking for spots, say for example, where f double prime is equal to 0, well, I'm looking for spots where my derivative of f prime is 0. That means I'm looking for spots where my slope of f prime is 0. Or in other words, I'm looking for spots where the slope of this graph right here is 0. Well, where do I have flat looking slopes? I've got one. I'll highlight this in a different color. I've got one flat looking spot right here. That's going to be a good spot for my second derivative to be 0. I've got another flat spot right here. This is going to be a good spot. And I've got another flat spot right here. Okay? So that means my spots that I really want to mark on this graph are going to be 2, 4, and 5. And I'll go ahead and kind of scroll down and give myself just a hair more room here to make a couple notes. What you are looking at to figure out the sign on the sign chart is what's going on with your slope of f prime. Okay, is your slope of this picture positive or negative? Now, if I'm looking at slopes on this interval back here to the left of 2, This function looks like it's decreasing. That means a negative slope. So a negative slope of f prime means a negative derivative of f prime means a negative second derivative. So if we're decreasing on this graph, it means we get to mark a negative. So that will be this interval from minus infinity to 2 and this interval from 4 to 5. This is the other spot where we're with a negative second derivative. And then my function was increasing on the other intervals. So what I can go ahead and note is that my concavity is actually switching up at every single one of these spots here. So this is going to tell me, you know, I'm concave down, then up, then down, then up. We are going to get inflection points at x equals 2, 4, and 5. Okay? And just to wrap things up, I'm going to give you guys a much more simplified version of this to take a look at on your own. Here's a quiz for y'all. If this is a graph of g prime, so you notice I have this labeled, this is y equals g prime of x, I'm asking you guys 2 questions. One, where, at what individual x value does g have a local maximum? You want to treat this just like the last question. Note, don't tell me 3. I will warn you right now, it is not 3, okay? G prime, this function that I've graphed, has a maximum at 3. I am asking about the original function g, so the thing that I took a derivative of to get this function. Where does that function, the original one, have a local maximum? And I'm also asking you also about the original function g, not this thing that I have a picture of here. Where's the original function g concave up? Okay, treat this kind of like the last question to get me that answer. So I want x value for part A, and I want an interval for part B. And also as a hint, I guarantee you there is an interval, okay, where this guy is concave up. If anybody has any questions, please feel free to let me know. We should start on with the next section next time.